Okay, so in terms of AnyLogic performance, I mentioned AnyLogic uses an event-driven scheduler. It goes from event to event to event, and making progress in simulating the model is defined by handling of these events. The more events, the more schedule per unit time, the more the scheduler has to wake up to do work more frequently. In order to, so to speak, in addition to work being done, there's some bookkeeping involved just in maintaining the events and their interconnections. For example, if a person dies, so one thing that may seem odd to you folks, but is a fact of that. If you ever run your model, watch this. I'm going to run this model, ABM model with birth death, and I'm going to go down to level. Oh gosh, I left that error in there. Maybe you can help me track it down. So what do I do to track it down? I click on this thing. Okay, it's going to bring me to that point. Where did that thing live? I could search using edit, search, and replace for this thing. Let's do that. My mother's age is, and search for this. Hey, come on. Why won't you select that? Come on. There we go. We can select this, search and replace, and it shows us where it is. Double click on it, and ba-boom, and I could disable it. But you know what, folks? This was just for illustration. I'm going to get rid of this. Boom. Boom. Dead. Okay. So let's run this model. Problem solved. So here we're running this model. We can go down to the level of an individual, and you'll notice that in this display, there's some interesting features. One thing is that we have these individuals shown in their current state, as highlighted in red for each state chart separately. And in some state charts, we'll actually show the amount of time that they'll spend in that state counting down. Okay, but you'll notice here that we have these highlights in blue. That illustrates the next transition that is anticipated to be led by this person. But those transitions may change over time. For example, in coming into this state, it calculated this transition will occur first. But maybe it turns out the person dies before this transition will occur, and we have to deschedule this event. This transition may occur first, but maybe some other one will end up preempting it. So here, there is some bookkeeping involved in maintaining the events. And if we have a greater occurrence of events, we'll often have really adverse effects on our performance. So some of you may have noted the very first model we ran in the boot camp of the expanding rings, those expanding annuli. Those grew slower in their expansion as they grew larger because there are more events being sent. There were just lots and lots of people infected, and infected people were sending events infecting others. Okay. So some suggestions here. You can, so lower event frequency. For example, you can use dynamic events as an alternative to static events under certain circumstances. You could do more on the firing of each event. You could disable them when they're not required, so they're not firing just in a useless way. Another thing you can do is send events only for infecting doses. We saw that the other day, and I've yet to show the statistics on that, on sort of why that's a good approximation. But the fact is that sometimes sending, 1/100th the number of events rather than sending 100 events with 0.01% chance of infection each, you send one event with sure chance of infection each. We may be able to save a massive amount of time in running the model. These are examples of sort of ways we could decrease events. Some of these have to do with other things here we'll be getting to and won't go into. So this is the example we talked about a little bit. These are context-specific considerations. Let's talk about statistics, however. Okay, so I'll end that with a